I want to take some time to show you how to verify trig identities. Now, verifying trig identities is going to seem very similar to simplifying trig expressions. However, they are a little bit different. Here's an example of a trig identity, secant theta times cosine theta equals 1. When we were talking about a trig expression, it would just be the left-hand side of this equation. But with a trig identity, that's going to be an statement involving trig functions that's true for all values of the variable. So no matter what angle theta is, if we take the secant of that angle times the cosine of that angle, it should always equal 1. But what we're tasked with doing is to prove that that is true. Now, kind of your general plan in proving or verifying a trig identity is to, I say, start with the ugly side, use your identities to change it into the pretty side. So when I'm looking at this identity, the left side is definitely the uglier side. To start off verifying an identity, you have to write that ugly side down exactly the way it looks. So secant theta times cosine theta. We can't change it at all. If we've changed it at all, we're proving some other identity. We have to prove this identity, which starts with secant theta times cosine theta. Now, I'm going to apply any trig identity or algebraic maneuver that I can to try and simplify this. And one thing that's always a good trig identity to use is to turn things into sines and cosines. For secant, the reciprocal of secant is going to be cosine. So then I'll have 1 over cosine times cosine. And of course, when we multiply these two together, those will cancel, and we're left with 1. So notice that we started with one side of the equation and transformed it into the other side. We started with the ugly side and turned it into the prettier side. We didn't use both sides of the equation at the same time. We start with the ugly side, turn it into the pretty side. So let's try a few more. Secant squared minus 1 over secant squared is equal to sine squared. The uglier side is obviously the fraction, so I'm going to start with that. Secant squared minus 1 over secant squared. Right. Leave it exactly the way it is. Don't change anything yet. Now, when I'm kind of planning out my attack for this problem, I can see a couple of different paths that will get me to the solution. I'm going to go through one. If you see a different path, it could be just as correct. It's a great thing about math. But what I'm going to do is I'm going to take this fraction and split it up into two separate fractions. Meaning I'm going to use secant squared over secant squared minus 1 over secant squared. Okay. So using that algebraic maneuver of subtracting two fractions. Then we can go ahead and simplify each of these fractions. Secant squared over secant squared, well, those will cancel out and leave me with 1. And then I have the reciprocal of secant squared, which is going to be cosine squared. Now we can use our Pythagorean identity. That is that sine squared plus cosine squared is equal to 1. So if I were to subtract cosine squared from both sides, right, then 1 minus cosine squared is going to be sine squared. Once I get to that sine squared that's on the right hand side, we can stop. Let's prove that 2 over 1 plus sine plus 2 over 1 minus sine is equal to 4 times secant squared of alpha. So I have to start with the ugly side, 2 over 1 plus sine, plus 2 over 1 minus sine. And we can't just, of course, say that it's equal to 4 secant squared. We got to start simplifying this thing. I've got two fractions that I'm going to add together. So algebraically, we have to get common denominators, which will be 1 plus sine times 1 minus sine. Which means in the numerator, the 2 that's in the first fraction has to get multiplied by the denominator of the second fraction, 1 minus sine. And the 2 that's in the second fraction, it has to get multiplied by the denominator of the first fraction, 1 plus sine. When we multiply this all out, we'll have 2 minus 2 sine, and distributing the 2 again, we'll have 2 plus 2 sine. And I know that a lot of you don't want to write out the denominator, but you have to every time. So here, but I mean, when I have 1 plus sine times 1 minus sine, that's the difference of 2 squares. So that's not too bad. But don't get lazy and ignore your denominator, because as soon as you get rid of your denominator, now you've made a statement that isn't true. Anyway, back to simplifying this thing. In the numerator, I have a minus 2 sine of theta and a plus 2 sine of theta that are going to cancel. So when we simplify the numerator, we'll just have 2 plus 2, which is 4. In the denominator, 1 minus sine squared. That should be standing out to you as a Pythagorean identity by now. That is cosine squared. And the reciprocal of cosine is secant. So those two fractions added together equals 4 secant squared of alpha. Let's do one more. 1 plus tangent squared theta times 1 minus cosine squared theta is equal to tangent. Again, there's going to be a couple of different ways to do this, but one thing that you have to do is to start off with the left side, that uglier side, exactly the way that it's written. So 1 plus tangent squared times 1 minus cosine squared. And you can maybe multiply that all out, but I recognize that both of those are Pythagorean identities. That 1 plus tangent squared is secant squared, and 1 minus cosine squared is sine squared. Since we have a secant and a sine, I'm going to turn them all into sines and cosines. Secant is going to be the reciprocal of cosine. And then we'll have multiplied by sine squared. When I multiply these two together, we'll have sine squared over cosine squared. And sine squared over cosine squared is tangent squared. And now we have it simplified. So we verified that the product is equal to tangent squared.